In this video, we will talk about what bipartite graphs are. So let's get right into a definition, which says that a bipartite graph is a simple graph. Remember, simple meant there's no multiple edges, no loops. Simple graph G, I'm going to call the vertices capital V and let capital E be the set of all edges. So it's a graph, simple graph, whose vertices can be partitioned. Partitioned means they can be split into two disjoint sets, V1 and V2. So I can split the vertices into two disjoint sets so that if I take the union of those two sets, well, it's got to be the original set, capital V, of all the vertices. But if I take the intersection, that's going to be empty. So what that means is, my graph would look something like this, V1 and V2, the set of two vertices. Well, there's no overlap between the two. But if I put them all together, if I union them, that gives me my set of all the vertices of the graph. Okay, well, what else has to be true about a bipartite graph? It says that every edge has one endpoint in V1 and one endpoint in V2. Okay, so let's draw an example. So any edge that I draw has to have one endpoint here, one endpoint here. So maybe this first vertex up here, maybe it's joined with this one, and maybe it's joined with that one. And maybe the second vertex is joined with three of the vertices on the other side. Maybe it's joined with this one, and with that one, and with that one. And maybe the third one is not joined with any other vertex with an edge. Maybe it's just isolated like that. This would be an example of a bipartite graph. Any edge that I have is always connecting one thing in V1 and one vertex in V2. Okay, so when this happens, we call this set V1 comma V2, we call that a bipartition of V, a way of splitting the vertices into two groups like this with no overlap, such that any edge that we draw will connect one vertex in V1 and one vertex in V2. Okay, so let's do some examples. So are the following graphs bipartite? And explain. Okay, so for each of these, I want to ask myself, well, is there a way to kind of split these vertices into two groups? Can I put them into one group and in a second group? So I'm going to think about that for both of these, such that any edge that I draw will always be connecting something in the first set with something in the second set. So I first want to give you an opportunity to try this. Pause the video for 3 minutes to try this. Pause it in 4, 3, 2, 1. Pause it and try that. Okay, so hopefully you did that. Hopefully you paused it to try it. So now let's come back and let's talk about it. So for this first graph, by the way, this is a special graph. This is a cycle. Remember, my notation for cycle is we call it capital C. There's three vertices, so this is C3. Part B is also a cycle with four vertices, so this is C4. Remember, a cycle is something that kind of starts at one vertex, and then the edges kind of go all the way around until they come back to the first one. Okay. And then when they do that, they end up hitting all the vertices along the way. Okay, so with this first graph with C3, no matter how I try to split these vertices up into my two circles, well, one of the circles for sure is going to have at least two vertices. There's no way for me to do it unless one of them has at least two. It's possible that maybe one of them has three and the other one's got zero, but for sure one of them's got at least two. And the other one, might have one at most. Okay, but if that was happening, because of the way the cycle works, there's gotta be an edge connecting these two vertices. And that would be problematic because for it to be bipartite, there can't be any edges within a circle. But I know based on the nature of the cycle, these would be connected and these would be connected. And well, the other two would be connected, but that's a problematic edge. So that's going to happen no matter what with C3. So for C3, let me give myself some room to write. For C3 here, the answer is no, it's not bipartite. No, it's not bipartite because in any bipartition, in any way of splitting the vertices into the two circles, at least two vertices will be in the same group. Will be in the same group. But that pair of vertices will be joined with an edge. So in this graph here, every pair of vertices is joined with an edge. But that pair of vertices is joined by an edge. Just because that's how this graph looks, any pair of vertices is joined by an edge in this graph. So as a result, this is not bipartite, because this is giving me this problematic edge. This is not bipartite. Okay, what about C4? What about this next graph? So for this one, I'm going to try a couple things. So let me copy this over because I'm going to try a couple things. So first, let me label the vertices here just because I got more of them. Maybe I'll call this A and then B, and then I'll have C underneath that and then D over here. So what if I first try to just like line it up like I got it right here in this square? So I'll put A here, B here, C there, D there, and now let's connect them just as they're connected right now. A to B, B to C, C to D, and D to A. Well, if I do that, there's two problematic edges. A to D, well, I have an edge connecting vertices that are in the same group. That's not allowed in a bipartite thing. And then from B to C, well, I also have a problematic edge. So does that mean it's not bipartite? Well, not necessarily. For it to be not bipartite, we have to show that no matter how I put these vertices into the two groups, that this problem will always happen. We've only shown that the problem happens in this one arrangement so far. Okay, so is there a way to move these around where it works? So maybe when you were trying the problem earlier, you were able to find a way, because it turns out it is possible. It's possible if you take two of the vertices, like C and D, and you swap them. So what if we were to keep A and B where they are, but then swap C and D? Because what should happen is there's an edge connecting A and B. There's an edge connecting C and D. There's an edge connecting A to D. A to D is now like this. Ooh, I like that. There's an edge connecting B to C, which would now be like that. Ooh, and if I can find one successful orientation like this, that makes it bipartite. So yes, this one is bipartite. So if I can find even one successful orientation like that, that makes it bipartite. So, for this first one, did we just look at one orientation and just automatically say it's not bipartite? Well, no, we didn't. Remember what we started off by saying was no matter how we tried to put the vertices into the two circles, for sure one of the circles was going to have two of them. And that was going to be a problem no matter what, no matter which way we tried to do it. And that's why we could say that no matter which way we tried to do it, all of them were not going to work. That's why this one is not bipartite. Okay, let's take a look at one more practice problem. So I have these kind of two overlapping triangles that we saw in the last video as well. So will this be bipartite? So, this one, hopefully we can see that, if I just focus on one of these triangles, like if I just focus on B to F and D, well, just from that one triangle itself, I'm going to have the same problem that I had in part A. So no, and the reason why is no, since we will run into the same problem among either of those triangles, but I'll just say among triangle, I'm going to put in quotes because it's not really a triangle. It's just, a subgraph, so to speak. It's among the triangle BDF. that we had in A, that we had in part A. Okay, having triangles like that creates problems when it comes to bipartite stuff. Okay, so the fact that there's a problem just from that triangle means that no matter what we do with any of the other vertices, that doesn't really matter. The first triangle already is a problem. The other vertices, throwing them into the mix, that's not going to fix the problem. So one of the questions that we might have is, well, is there some other way to tell if a graph is bipartite? Rather than having to kind of do casework like this each time. And it turns out, yeah, there is a way to tell if a graph is bipartite. We'll need to introduce a bit more terminology, and this has to do with the idea of colorings in graph. There will be a connection between colorings and if a graph is bipartite or not.